Okay, so let's look specifically at some binary phase diagrams. And in particular, let's first note that we had discussed in the last class that the number of degrees of freedom is equal to, by the Gibbs phase rule, is given by C minus P plus 2, right? So we know that if the number of constituents is 2, then the number of degrees of freedom is given by 4 minus P, right? Now, this gives us a little bit of a problem, because that means if we have only one phase present, in general we have 3 degrees of freedom possible. So typically, to draw a binary phase diagram, and typically we want to draw such a phase diagram on a 2-dimensional piece of paper, so displaying 3 degrees of freedom would be difficult, we fix the pressure. And typically we fix the pressure at 1 atmosphere. So you could make a phase diagram for different pressures. So this reduces the degrees of freedom. So in that case, we have our new number of degrees of freedom, F prime, which is equal to F minus 1. So that's going to be C minus P plus 1, or in the case of a binary phase diagram, this leads to F prime equal to 3 minus P. So if we have one phase present, then we have 2 degrees of freedom. Okay, so that's important when you look at these binary phase diagrams. They're for a specific pressure. Okay, so let's first look at our ideal mixture. And so this is part of the phase diagram we put up initially, has this ideal mixture character. So in an ideal mixture, we typically get a phase diagram that looks like this. So we have a function of temperature, and then we have our composition. We'll call that XA. So here we have pure A, and here we have pure B. And we said that that meant that over here somewhere we have the melting temperature of pure B, and over here we have the melting temperature of pure A. And that way above this, we have the system is entirely liquid, and then we have a liquidus line that describes at what temperature we start forming solid at various compositions. So this is, we said, our liquidus. And we have a solidus line that describes at what temperature we begin to form solid. And so we said that this region of the phase diagram is liquid plus solid, and this is fully solid. Okay. So this is our typical ideal mixture phase diagram. And if one thing to review, most of you have probably seen this before, if you want to determine the composition of the 2 phases present in the liquid plus solid part of the phase diagram, it's possible to use the lever rule. So if we started here, let's say at this composition, so some composition here, and we started decreasing the temperature, initially we would have a homogeneous liquid, but if we decrease the temperature to some temperature here, right, then we wouldn't have pure liquid, we would have liquid and solid, right? And so we could ask, what is the composition of the liquid and the composition of the solid, and what are the numbers of moles of liquid and solid available? Well, we know at this temperature, this is the composition, so this is our net composition, right? This would be our composition of the solid, right? And this would be our composition of the liquid present at that temperature, right? And then it turns out if we measure the lengths of these lines, so let's call this d sub s for the distance between the composition and the composition of the solid, and call this d sub l for the length between the net composition and the composition of the liquid, it turns out that the number of moles of solid over the number of moles of liquid has to be equal to dl over ds. So we can figure out from the phase diagram both the compositions that are present and the ratio of the moles. And we can show this has to be the case by noting that the number of moles times the net composition, right, has to equal the number of moles of the solid times the composition of the solid plus the number of moles of the liquid times the composition of the liquid. We know that the total number of moles has to equal the number of moles of the solid plus the number of moles of the liquid, right? Now if we subtract one of these from the other, right, we get that the number of moles of the solid times the net mole fraction minus the number of moles of the solid, right, has to equal the number of moles of the liquid times the composition of the liquid minus the net composition. And this is essentially ds, and this is essentially dl. Okay, so that gives us our lever rule. Okay, but one thing we could ask is, where does this shape come from? Why would we expect to get this kind of shape in the ideal mixture? And the way to think about that is by thinking about the Gibbs free energy as a function of composition. So we're going to write this again as XA, and now we're going to write the Gibbs free energy of mixing as a function of XA, and we're going to do that at several temperatures, right? So this will be at, so let's define some different temperatures. So let's call this let's start T1, it'll be the highest temperature. T2 will be somewhere in the middle. T3 will be somewhere further down, and T4 will be in the solid. Okay. So let's draw some curves like this, some places to put curves. So this will be our delta G versus XA. And these will be for our 4 different temperatures. So let's start first at T1, which is this highest temperature. So at this highest temperature, at high temperature, we know that the liquid has a lower free energy right, at high temperature than the solid. So this is our G of the solid. This is our delta G of the liquid. And since the liquid is always less than the solid, we know the liquid will always be the favored phase, and so we just always have liquid. So that's very simple, right? And actually I should draw this more like this. Okay, so what happens now at T2? Let's go to T2. At T2, something funny has happened. Now we have both liquid and solid, right? So we know that on this part of the phase diagram, the solid is lower in free energy than the liquid. So we have solid here. And at this side, the liquid is lower in free energy. So we have a free energy diagram that basically looks like this. Okay, so here we have, I'm going to just draw these, fill these in. So here we have delta G of the solid. Here we have delta G of the liquid. And what we note in this region is that there's some region where it's possible to draw a line that connects the two free energy curves and lower delta G by creating a mixture of the two phases. So now remember, if we draw a line, right, on a free energy versus composition diagram, the intersections of the line with the two axes on either side give us the chemical potential of the B constituent and the chemical potential of the A constituent. So if we can draw a tangent that goes through both of these points, that means the chemical potential of A and B at this point are equal to the chemical potential of A and B at this point. And if that's the case, then those two can coexist. And they can coexist at any composition that falls along this line. So this is, so what we're going to say is that the common tangent describes a pair of liquid and solid compositions with equal chemical potential. And so it turns out that above this composition, you'll have just the solid, right? Along this line, you'll have the solid and the liquid. And then along this line, above this composition, you'll have pure liquid. And so that's what's happening here. We're going from being on the green curve over here to being on the red line that joins the green curve and the blue curve, to being on the blue curve as we move over here. Right. Now, as we continue to decrease the temperature, so now as we go to T3, now recall the entropy of the liquid is higher than the entropy of the solid, so as we go to a lower and lower temperature, the free energy of the liquid is less and less favored. So the liquid curve will move up compared to the solid curve. So now maybe the solid curve is here. Okay. And again, we see there's a place where we could draw a tie line. And how do you know you can possibly draw a tie line? Well, it turns out if you look at the locus of points that describe the lowest free energy, it has to be convex, right? So the curvature has to be such that it's always bowing out. And notice here you have a concavity, right? It goes in and then it comes out again. So this locus of points that we're forming is called the convex hull. Okay, so this is our convex hull. And in this case, it consists of the liquidus here, right? So this corresponds to the points. Now we're at T3, from here to here, right? We're on the green curve. then from here to here, we're on the red curve. So that corresponds to here. That's on our convex hull. And then from here to here, we're on the blue curve, right? And so that denotes the composition at which we start having solid-liquid coexistence and the composition at which we start having fully liquid, right? So this is our delta GL, and this is our delta GS. Okay. And then finally, at T4, right, we've gotten to the point where the liquid free energy is fully above the solid, and then of course we don't have any tie lines anymore, we just stay on the solid free energy curve. Okay. Good. So the important points here are, when you have free energy curves and you can plot them at different temperatures, it's important to look to see if they intersect, whether there are any points that are concave, and that the locus of free energies that describe the low energy of the system can't contain any concave segments. And so what you must do is draw a common tangent, and the common tangent gives you a region where you can have two-phase coexistence, and the locus of points consisting of the convex portions of the pure phases plus the common tangents gives you the convex hull that describe the lowest free energies the system can have at various compositions.